The universe is one of the most fascinating and mysterious subjects in science. It contains everything that exists, including galaxies, stars, planets, and all forms of matter and energy. But just how big is the universe? To answer this question, we must first understand the concept of the observable universe. The observable universe is the portion of the universe that we can see from Earth. It is limited by the speed of light, which means that we can only observe objects that are within a certain distance from us. According to current estimates, the observable universe has a diameter of approximately 93 billion light-years. This means that the most distant objects we can see are approximately 46.5 billion light-years away from us in any direction. However, it's important to note that the universe is expanding, which means that the distance between objects is increasing over time. Beyond the observable universe lies the unobservable universe, which we cannot see or observe in any way. The size of the unobservable universe is unknown, but it is believed to be much larger than the observable universe. Scientists believe that the unobservable universe may contain regions that are similar to our own observable universe, with galaxies, stars, and planets. One way to visualize the size of the universe is to consider the number of galaxies it contains. Current estimates suggest that there are between 100 billion and 200 billion galaxies in the observable universe alone. Each of these galaxies contains billions or even trillions of stars, and many of these stars have their own planets and other objects orbiting them. Another way to think about the size of the universe is to consider its age. The current estimate for the age of the universe is approximately 13.8 billion years. This means that light from the most distant objects we can observe has been traveling towards us for over 13 billion years. The concept of the observable universe was first proposed by Belgian astronomer Georges Lemaitre in 1927. Lemaitre's theory was based on the idea that the universe was expanding, and that the farther away an object was from us, the faster it was moving away. This theory was later confirmed by American astronomer Edwin Hubble, who observed that distant galaxies were indeed moving away from us at high speeds. As our understanding of the universe has grown, so too has our ability to observe it. In recent years, advances in technology have allowed us to study the universe in greater detail than ever before. For example, the Hubble Space Telescope has provided us with stunning images of distant galaxies and other objects in space. Despite these advances, however, there is still much we do not know about the universe. For example, we do not yet understand what dark matter and dark energy are, even though they are believed to make up the vast majority of the universe's mass and energy. One of the most intriguing questions about the universe is whether or not it is infinite. If the universe is infinite, then it would contain an infinite number of galaxies and stars, and there would be no edge or boundary to the universe. However, current evidence suggests that the universe is finite in size, although it is still much larger than we can comprehend. Another interesting fact about the universe is that it is not uniform in its distribution of matter and energy. Instead, there are regions of the universe that are denser than others, and these regions have a greater gravitational pull. These dense regions are known as galaxy clusters, and they can contain hundreds or even thousands of galaxies. In the early 1900s, the universe seemed to be a much smaller place. Back then, astronomers believed the Milky Way galaxy was all there was. They didn't know there were billions of other galaxies. They didn't know how small we really are. They didn't know this because they couldn't measure distances to far-flung stars. Why? There was a pretty simple problem in astronomy. A bright, far-away star looks almost the same as a dim star that's close by. It's the same here on Earth. Imagine you're on the beach at night and see two lighthouse lights glowing in the distance, but one seems brighter than the other. If you knew both lighthouses use the same light bulb, You could conclude that the dimmer light is farther away. But it's also possible that the dimmer light just comes from a lower wattage light bulb, perhaps nearer to you. Scientists needed a way to find out the intrinsic brightness of stars to figure out their wattage, so to speak. That's when Henrietta Leavitt, a Massachusetts-born computer who worked at the Harvard College Observatory, came along. In 1908, she published a discovery that may sound small but is one of the most important in the history of astronomy. Before Henrietta Leavitt, many astronomers looked at the stars in what's today known as the Andromeda Galaxy some 2.5 million light-years away and mistakenly thought they were part of our own Milky Way galaxy, which is only around 100,000 light-years in diameter. Those Andromeda stars were orders of magnitude further away. Scientists just didn't know it. At the time, astronomers had some methods to figure out distances to stars, but they only worked for stars relatively close to Earth. Leavitt's discovery linking the pulse of one type of star to their actual brightness, as described in the graphic above, was the key to measuring objects farther and farther out into space. If astronomers wanted to measure faraway things, Leavitt's discovery showed, they just had to look out for Cepheids. Her formula led astronomers to chart out relative distances to stars. They could use it to compare to stars and figure out which one was closer. It took some more work by other scientists to calibrate this yardstick, to put concrete numbers on it. But once they did, and started measuring with it, the cosmos grew and grew. 15 years after Henrietta Leavitt's discovery, the preeminent astronomers Harlow Shapley and Heber Curtis were locked in a heated debate. Curtis believed that Andromeda was a separate galaxy far, far away from the Milky Way. At the time, this was an outlandish idea. Shapley represented the more mainstream view that Andromeda was just a hazy, cloudy region within our galaxy, which he had recently estimated to be around 300,000 light-years across. That was also the assumed size of the entire universe. If Curtis was right, it would mean the universe was double or triple the size that Shapley estimated at least. To settle the debate, Edwin Hubble, the namesake of the famous space telescope, looked for Cepheid stars in Andromeda. Night after night, he took photographs of Andromeda, searching for Cepheids. In October 1923, he found one, blinking in one of Andromeda's spiral arms. Another week of observations allowed him to follow Leavitt's formula and determine its distance. Hubble estimated it to be around 1 million light-years from Earth, well outside the boundaries of Shapley's universe. Hubble was a little off. Andromeda is closer to 2.5 million light-years away. After reading about Hubble's finding, Shapley reportedly said, "Here is the letter that destroyed my universe." Scientists kept building on Leavitt's ruler to measure the universe, and as they used these measuring tools, their understanding of the universe evolved. They realized it was far bigger than previously thought. There are billions of galaxies, and it's expanding. Those galaxies are moving further and further away from one another. Astronomers also realized that the universe had a beginning. If galaxies are moving away from one another now, it means they were closer together in the past, which led scientists to the idea of the Big Bang. Every day, our cosmos gets bigger and bigger, with the average distance between galaxies always getting larger. So far, so good, right? But that expansion isn't caused by galaxies moving in the universe, but rather the space between the galaxies expanding. If you were to attach an accelerometer to every galaxy, they would register zero movements except for small, local motions here and there. Locally, no galaxy is moving, but the space between them is. So there are no restrictions here based on the speed of light because they're literally not moving. There's no limit to how quickly space can expand because expanding isn't motion as far as relativity is concerned, and so the universe can grow as quickly as it pleases. The light from galaxies beyond the Hubble radius was released billions of years ago and is only just now reaching the Earth. We calculate where these galaxies are right now based on our understanding of cosmology, and that's how we're able to estimate the size of the universe. If you enjoyed this video, please like and subscribe to the channel, and don't forget to watch other best videos that we made for you. Thank you.